In this series, we'll take a look at the main concepts behind neural networks. We'll walk step by step through both forward and backward propagation of a simple network, training it to recognize handwritten digits, and later apply that theory by implementing it in NumPy. But first, let's understand the problem. The MNIST database, which we'll work with, is a collection of 70,000 28 by 28 pixel handwritten digits. Each pixel has a value from 0 to 255, representing its brightness. Now, given an image, the goal for the network is to predict what number appears in it. So here, our network should predict 7, 3, and 0 here. To formalize the problem a little, we want to create a neural network that takes 784, that is 28 times 28, values representing brightness of each pixel, and we want to return the probability of each class. In this case, we want the network to output probability of each digit. Then, the number with the highest probability will be the one the model thinks is on the screen. But before we really tackle with MNIST, let's just talk about what neural network is and consider a simpler example. To understand a neural network, we must first understand what the fundamental building block of a neural network is. That is, a neuron. It actually consists of two parts, a linear part and an activation function. A linear part simply multiplies the weights and inputs and adds a bias. The result of the linear part then serves as an x-coordinate for an activation function, which later becomes the output of a neuron. Now, the activation part may seem a little confusing, and we will get back to that later, but for now, just know that an activation function allows the network to learn more complex dependencies, and that it has to be nonlinear and continuously differentiable, with some exceptions. For now, let's define a sigmoid activation function. As you can see from the graph, it has a distinct S-shape and a range between 0 and 1. It isn't as popular as it once used to be. Functions like tanh and ReLU are far more common nowadays. However, I picked it because you may have already encountered it while studying logistic regression, and because it has a very simple derivative, which will later make it easier to implement. Now, this was very theoretical, so once again, let's play with a single neuron and plug some values. It has weights, bias, and a sigmoid activation function. So first, we multiply our input by weights, add a bias, plug that into an activation function, and voila! That is the output of our neuron. Now, the input of the neuron will most likely be a vector, not a single value. So let's look at an example where x is a vector. Fortunately, not much changes. We just take a dot product of the weights and inputs, add a bias, and plug the output into an activation function. And that's it for a single neuron. Now, what makes neural networks so universal is that we can actually stack those neurons together to create a layer and use the output of the previous layer as an input for the next one. By that, allowing the network to learn more features like edges or shapes. Let's take a look at that. Imagine we are given 3 inputs, a wingspan, mass, and average flight velocity. Our goal is to correctly predict bird species, peregrine falcon, a house sparrow, a white-tailed eagle, and American crow. We'll use a very simple network so we can go step by step through every operation. We start with 3 inputs, we pass them to a layer consisting of 2 neurons, then we pass those to another layer, this time made of 3 neurons, and after that we pass it to the final layer. Note, we refer to the first layer as an input layer, the last one as an output layer, and layers in between are called hidden layers. In this example, the network is already trained. That means it has all the weights and biases optimized and should produce correct results. We'll cover how those parameters are optimized in the second part. But for now, let's look at the data. We can see that we are provided a wingspan, mass, and average flight velocity, as well as the correct class. To see if the model's prediction was correct, let's plug the values from the first row. Looking at the first neuron of the hidden layer, take the dot product, add a bias, pass that through our sigmoid function, and that is the output of the first neuron. We do the same thing for the other neuron, which remember has different weights and a different bias, and we get an output of the second neuron. Now we pass those outputs from the first layer as inputs to the second layer. So now, looking at the first neuron of the second hidden layer, we take the output from the first hidden layer and multiply it by weights, add a bias, and pass it for sigmoid. We repeat this step for the other two neurons. And finally, we do the same thing for the output layer, but now using outputs from our second hidden layer as input, and we will not be using sigmoid activation function. Finally, after forward propagating through our network, we get some numbers. These are usually called logits when talking about classification tasks, but they don't look like they mean much. We usually want our output to be between 0 and 1, and the sum of all outputs to be exactly 1, representing probability. It makes things much easier to interpret. Fortunately, there exists a function that does just that. The softmax function. It might look a bit intimidating, but let's just apply it to the output layer and see what we get. So, for the first neuron, you raise e to the power of the logit for the crow and divide it by sum of e's raised to the power of logit from each class. So e to the logit of a falcon, plus e to the logit of an eagle, plus e to the logit of the crow, and plus e to the logit of the sparrow. Let's do the same for a second neuron. The denominator stays the same, we just change the numerator to e to the power of a logit of an eagle. Repeat the same operation for the next two, and finally, we have officially went through the forward propagation. You can check that all the outputs are between 0 and 1 and sum up to 1. We can also see that the eagle class has the highest probability, aligning with the actual label of the data. That means our model correctly predicted the bird species. Unfortunately, now we have to formalize the intuitive understanding a bit. We can replace calculating output for a single neuron individually by multiplying the weight matrix composed of weights from each neuron in a layer by the input. That way, we can calculate the output of a layer in one go rather than having to perform the computation individually for each neuron. For notation, we will use z with an upper index to indicate the linear part of the layer. So z1 is the linear part of the first hidden layer, z2 of the second, and so on. We will use w with an upper index to denote weights of the layer, and b with an upper index will be the bias for that layer. Sigma will be our sigmoid function. Similarly, A with upper index represents output of an activation function for that layer, and X will be our initial input. Now, let's write the forward propagation mathematically. Z1 is the linear part of the first hidden layer, that is W1 times X plus B1. We pass that to the activation function, so A1 equals to sigma of Z1. Now A1 is the output of the activation function, but also of our first hidden layer. Now for the second one. Z2 is equal to W2 times A1. Remember, we use output of the previous layer as an input for the next one, plus B2. And A2 equals to sigma of Z2. Now we pass it to our output layer, so Z3 equals to W3 times A2 plus B3. Difference being that now A3 is softmax of Z3. Alright, now that we have written the equations for forward propagation, it would be nice to analyze the shapes of every part, because since we are doing computation for layers instead of individual neurons, we are dealing with vectors and matrices. Let's see what we know. X is a 3×1 vector. Now, what is W1? Remember, we have 2 neurons in the first hidden layer and 3 inputs. Every neuron must have a weight for every input. So our weight matrix will have 3 columns, 1 weight per input, and 2 rows, 2 neurons. Now, what will be the shape of B1? Well, every neuron must have 1 bias, so it is 2×1. So what shape must be Z1? It must also be 2×1, as it is a linear output from 2 neurons. We also know W1 and X gives us a 2×1 vector, and adding a bias does not change the shape. What about A1? Well, notice that this is just our activation function and does not change the shape at all, so we stay with 2×1. Now what about W2? Well, A1 is 2×1, so we know we need 2 columns again, because there are 2 inputs and every input needs a weight. And 3 rows, because we have 3 neurons. Z2 must have the same shape as W2 times A1. We see that Z2 is a 3×1 vector, and so is B2. A2 remains 3×1. And now for Z3. There are 3 inputs and 4 neurons. So W3 is a 4×3 matrix. Multiplying W3 with A2 gives us a 4×1 vector, and that is the shape of Z3 and B3. As for A3, the fact that we use softmax function instead of sigmoid does not change the rules of the game. A3 also has a shape of 3×1. Finally done. We trudged through shape analysis. If you still don't feel comfortable, feel free to rewatch this part until you do. While tedious, it is important to grasp the shape of each component and the reason why it's that way. Here's a different neural network. If you want to test yourself, try to do a shape analysis on your own and compare to an answer I will display in a second. Here it is. Okay, now we are going to introduce a very important concept. We'll get to training a neural network in a second, but for now, all we need to know is that our data usually has some noise in it. Said noise hinders the convergence of our training algorithm. Sounds scary, I know, but trust me, in the next part is all going to make sense. One way we combat the noise is we process several inputs, in our case observations about birds, at once to minimize the noise. This technique is called batching. Let's see how this works in our example. X is now a 3 by m matrix, where m is the number of examples in a batch. The shape of our weights remain the same. For example, the shape of W1 is still 2 by 3. The product of W1 and X has a shape of 2 by m, and so does Z1. So far so good, but there's a problem here. A shape problem to be exact. Take a look at B1. It still has a shape of 2 by 1, but our product has a shape of 2 by m. We cannot add those two, but we also do not want to add additional biases. Those would be another parameters to optimize, plus the number of parameters would depend on the batch size, and we want to avoid that. So how do we go about solving this problem? Well, we simply stack the bias m times. That way, we have a new 3 by m matrix B1 tilde. But we didn't add any new parameters, we just reused the ones we already had. This technique is called broadcasting. Alright, now that we've fixed the shape issue, the rest of forward propagation is pretty much the same. So I will not go over the entire shape analysis step by step again. If you feel like it, you can try it yourself and see if you got it right. Alright, that's it for this part, but before we go, I will show, as promised, why the activation function is important. The best way to answer that question is to see what happens when we don't use an activation function. So let's use our network as an example. We'll set an identity function as an activation function. Just to keep the notation, the identity function returns input as output, not changing it at all. But now, since there is no activation function, A3 equals Z3 equals W3 A2 plus B3, and again, since A2 equals to Z2, that is equal to W3 Z2 plus B3. If we repeat this process, what we end up with is a nasty looking operation. So let's define capital W as well as capital B. And we see that what we got is just a linear regression. Without an activation function, the network isn't capable of learning nonlinear relationships. Right. So far, our weights and biases were already optimized, which means they already predicted the correct class. But how do we tune those parameters? In the next part, we'll cover just that. Thank you for watching. If you liked the video, please like it and subscribe to the channel. If you have any questions, feel free to leave a comment and I'll try to answer it as soon as I can.